Darasa Online.
Hello my dear students, how are you? My name is Josiah Mwaktalima. I'm a chemist teacher from Kibaha Secondary School. I'm here to discuss some concepts or issues in chemistry subjects that are mostly difficult or it seems to affect most of you. So for today you are going to start with a topic known as relative molecular mass in solutions. So this is our main topic, and this topic have two main subtopics, that is the properties of colligative and the laws governing colligative properties. Today we are going to start with a subtopic known as laws governing colligative properties. So under this subtopic, at the end of this subtopic, every one of you should be able to calculate or to determine the degree of dissociation of strong electrolytes. And the competence that you'll gain from this subtopic is that you'll be able to apply the chemical method and design possible approaches that will help you to solve different problems that are happening in our normal life situation. So you are warmly welcome and make a follow-up on it for you to benefit from this lecture. Now, let me recall you back from what we discussed about colligative properties. We saw that there are conditions for a solution to obey the colligative properties. And these conditions, one is that the solute must be non-volatile. Second, the solution should be dilute. And the third is that the solution should neither dissociate nor associate, which means that the solution should be non-electrolyte. Now, all these conditions, any solution that obeys these conditions are now subjective to what we call it colligative properties. And the application of these colligative properties is in the determination of relative molecular mass of the solution. So the colligative properties equations are used in determining the relative molecular mass of a solute in a solution. And as what we have said here, that the solute should neither dissociate nor associate, and it should be dilute. So what will happen now if the solution or the solute undergoes association and dissociation? So under this condition, if the solution undergoes association or dissociation, the colligative properties that we discussed cannot be applied, because normally a solution which undergoes dissociation or association its molecular mass changes. That means it can be large or it can be smaller, whereby if a solution undergo dissociation, so when a solution undergoes dissociation, its relative molecular mass becomes lower than the expected molecular mass of that solute. And if a solution undergoes association, its relative molecular mass becomes larger than the molecular mass expected of that solute. Now consider, if now a solution undergoes dissociation, how will you determine its relative molecular mass? If a solution undergoes dissociation or association, a Van 't Hoff's factor is introduced into colligative properties equation, and the Van 't Hoff's factor is denoted by small letter I. And the Van 't Hoff's factor is calculated by taking the ratio of the observed osmotic pressure over calculated osmotic pressure or expected osmotic pressure. So Van 't Hoff's factor is determined by taking the observed colligative properties dividing by its expected or calculated colligative properties. You remember now about these colligative properties. So if it is lowering of vapor pressure, it will be the observed lowering vapor pressure then divided by expected vapor pressure. If it is about boiling point elevation, then the Van 't Hoff's factor will be calculated by taking the observed boiling point elevation then dividing by calculated boiling point elevation. And if it is about freezing point depression, then you will take the observed freezing point depression then dividing by expected freezing point depression. Then if it is concerned about osmotic pressure, will be the observed osmotic pressure then divided by calculated osmotic pressure. Now, for due to dissociation, due to dissociation of strong electrolyte, the Van 't Hoff's factor is determined by taking the total number of moles or of particles during dissociation dividing by the total number of particles before dissociation. So now let us consider that you have a strong electrolyte AB with a degree of dissociation alpha. Now alpha, since AB since is our strong electrolyte, it will dissociate to release A ions and B ions. So these are our ions that have dissociated from the strong electrolyte, which is AB. Now remember that initially the amount of strong electrolyte present was 1, and after dissociation a certain amount of our strong electrolyte will be dissociating into its ions, that is product. So to determine the total number of moles before dissociation, that means you take 1 plus 0 plus 0, then ending up to get the total number of particles, which is 1. And to obtain the total number of particles after dissociation will be 1 minus alpha plus alpha, then plus alpha. So you now have obtained the total number of moles before dissociation and the total number of moles after dissociation. Now to find the Van 't Hoff's factor, we have said that you just take the total number of moles after dissociation, you divide by the total number of moles before dissociation. And the number of moles before dissociation is 1. And the total number of moles after dissociation is 1 plus alpha. So for the Van 't Hoff's factor for our strong electrolyte AB will be now equals to 1 plus alpha. And mind you that if the Van 't Hoff's factor obtained is greater than 1, it means that the solution will be undergoing dissociation. But if the Van 't Hoff factor I obtained is less than 1, it means that the solution will be undergoing association. And if I is equal to 1, then there is neither dissociation nor association. Therefore, to determine the relative molecular mass of a solution that undergoes dissociation or association, we have to use Van 't Hoff's factor, and that is how it is being calculated. And Van 't Hoff's factor now is introduced into the colligative properties equation, which are that of lowering vapor pressure, freezing point depression, boiling point elevation, and the osmotic pressure. So the data given, we have the concentration of the solution. We have the osmotic pressure. This osmotic pressure is the observed osmotic pressure, and this is the expected or calculated osmotic pressure. But there we have given the solution that we have supposed to calculate its degree of dissociation is calcium chloride. But first you have been asked to calculate the Van 't Hoff's factor, which is I. As what we discussed, to determine the Van 't Hoff's factor, we just take up the observed osmotic pressure over expected osmotic pressure. So if we substitute our data that we have been given there, now if you substitute into our calculator, then the answer that you will get it, this is now 0.605 divided by 0.224. The answer is 2.7. Therefore, the Van 't Hoff's factor for this solution is 2.7. Now, the second part, you have been asked to calculate now the degree of dissociation. Then the degree of dissociation of our solute, which is calcium chloride. Normally here calcium chloride dissociate to release calcium ions and 2 chloride ions. So if we refer to the dissociation equation of calcium chloride, and initially there were 1 or 100% of calcium chloride present, which means that calcium ions there were no 0 and here there were 0. But after dissociation, a certain amount of calcium chloride were dissociating into its ions. Here will be alpha, here there will be 2 alpha. 2 because of the 2 number of moles of chloride ions. But here is 1, that's why it's alpha. Here is 2, that's why we have put it 2 alpha. Now the total number of moles after dissociation and before dissociation. So the total number of moles after dissociation is 1 plus 2 alpha. Now from Van 't Hoff's factor, total number of particles after dissociation divided by total number of moles of particles before dissociation. From there now, by making alpha the subject, which is our unknown variable, which is the degree of dissociation, so the degree of dissociation will be found by taking the Van 't Hoff's factors minus 1, then divide by 2. Now, if we substitute, since we have got the Van 't Hoff's factor, so if we substitute now those data into our equation, 2.7 minus 1, then divide by 2, the answer is 0.85. Or in degree, or in percentage, it is 85%. So this is what we call it our degree of dissociation for calcium chloride. So do you see now the question is so simple once you consider what you are supposed to do before tackling it. So now we can proceed to the second example. Now if we consider the second example, the question is calculate the osmotic pressure of an aqueous solution of barium chloride at 298 Kelvin containing 0.39 gram in 60 cubic centimeter. The degree of dissociation of salt is 60%. So the data given now from that example now from our data now, we have mass of barium chloride, volume which is 60, degree of dissociation which is 60, which is equal to 0.6 also. Now what we been asked is to calculate the degree of dissociation. Given the degree of dissociation, we have been asked to calculate the osmotic pressure of an aqueous solution. Now so if we go back to refer to colligative properties, osmotic pressure were being calculated by taking the concentration times molar gas constant and times the temperature. But since our solution undergoes dissociation, then we have to introduce what we call it Van't Hoff's factor for determination of osmotic pressure. So if we observe now from our example and the data given, we have the degree of dissociation, we don't have the concentration, but we have the molar gas constant, and we have also the temperature, which is given as 298 Kelvin. Which means that here now we have to find out the concentration of our solution. Now the concentration of our solution can be calculated from So we calculate the concentration in moles per decimeter cubic by taking the number of moles of solute over volume in decimeter cubic. But still here the volume we have, because it is this one that we have been given, which is 60 or equals to 0.06 decimeter cubics, but we don't have the number of moles. And if we don't have the number of moles, how are you going to find it? Just simple. You just the number of moles So the number of moles, you just take the mass given and then you divide by molar mass. And the molar mass of our solution, which is barium chloride. Which is now barium is 137 and chlorine is 35.5. Since there are 2 chlorine, then it will be 35.5 times 2. So if we now use our calculator to find the total, the answer is 280. This is gram per mole. Now we have the molar mass and the mass we have already given, which is 0.39 grams. So now if we use our calculator also to calculate the number of moles, now 0.39 divided by 280, then the answer is 1.875 times 10 power negative 3. This will be moles. Now you have got now the number of moles that we are finding, so that you can define it, we can divide it by the volume in decimeter cubic. So if we divide now the number of moles by volume, the concentration obtained is 0.03125, that is moles per decimeter cubic. Now this is our concentration that we have now to substitute in Van 't Hoff's equation. If we recall from Van 't Hoff's equation, osmotic pressure is equal to Van 't Hoff's factors times concentration times molar gas constant, then times temperature. And the Van 't Hoff's factor can also be calculated from so from Van 't Hoff's factor, I is equal to total number of particles after dissociation divided by total number of particles before dissociation. But alpha, which is the degree of dissociation, given is 0.6. Now, if you calculate using your calculator, I'm sure you'll also get 2.2. So that is our Van 't Hoff is factor. That now we can now go back to our equation for determination of osmotic pressure that you have been asked. So if we substitute these data into our equation, so if you use your calculator, my dear students, I'm sure you'll have the same answer as 2.2 times 0.03125 times 0.0821, then times 198 Kelvin. The answer is 1.0 682. The units now here will be atmosphere. Atmosphere meaning that per decimeter will cancel with the decimeter cubic, and per Kelvin will cancel with the Kelvin, and the mole will cancel with the per mole. Here we have per mole. That will cancel with this one. Now the answer will be now 1.682 atmosphere, which is now the osmotic pressure of our solution that have undergone dissociation. Now that is how you can calculate the degree of dissociation, as well as application of the degree of dissociation in the determination of the relative molecular mass, or any kind of colligative properties that you'll be asked to calculate. Now from there, let us go to the real life situation for application of the colligative properties, as what we discussed earlier, that the colligative properties, the main application is one in determination of relative molecular mass of solute in solution. For now, we are going to see the application of colligative properties in our real life situation. That's why at first I told you that at the end of this lesson, you should be able to apply chemical method and design possible theories to solve different problems that are taking place in our normal life situation. And remember that the colligative properties, we have lowering vapor pressure, we have freezing point depression, we have boiling point elevation, and we have osmotic pressure. So we are going to look now some of the application of these mentioned colligative properties in our real life situation. Now to overall our topic and see how it can be applied in our normal life situation is that the application now of colligative properties as a whole. One, it is used in road sorting. In road sorting refers to the process of spreading out the salts on ice, that the ice now will melt to release water, and then now there will be no longer ice there. Let us see now from the example here. This is an example. You see now the ice are dropping down on the surface of the earth. Now cars are going to the stores for taking out the salts. Salts now are being poured into a car and ready now for spreading out on road surface, so that they can lower the melting point of the ice.
The story of road salt begins around the end of World War II. Detroit, Michigan was the first to begin widespread use of the substance as a de-icer. This was due to the state's sprawling road and highway systems, a result of the auto boom, as well as the city's proximity to one of North America's largest salt mines right beneath it.
Yeah. Now, do we see now the highways are being now spread? The cars now are spreading on the highways the salts, and those salts are there to lower the freezing point of ice, so that there can no longer be again ice on road surface. Therefore, cars can now continue passing without any obstacles, since now ice have melted. So that is what we call it freezing point depression. Okay, another application of colligative properties is applied in car radiator. So the knowledge of colligative properties is also applied in car radiator, especially for those countries that experiences a winter season, a heavy winter season, whereby the car in the radiator are not freezing. You can ask yourself, why are they not freezing? Let us see now what is being done. Now, do you see now that is a water now to put into a car radiator? But that is a solution now which is mixed with the water so as to prevent it from freezing, and that is known as ethylene. So that is the distilled water that should be mixed with those two solutions that lowers the melting point of the water. So that is now how the two solutions can be mixed into car radiator. Therefore, even during winter season, the water do not freeze. So then the machine then can proceed working, and the car can proceed just being driven through under that condition where the temperature or the country experiences a very low temperature that results into formation of ice or into freezing of water that are present in that area. So another application of colligative properties is applied in purification of seawater by what we call it using osmotic pressure, or sometimes the method is known as reverse osmosis, where you can obtain pure water from seawater. So as you, our expected engineers, you now have this knowledge and apply it in finding out or in driving out seawater into our environment and convert it into fresh water for using purposes in our homes. So it is used also in purification. In purification of sea water by reverse osmosis. So let us see now how can you purify seawater by using reverse osmosis. Okay, let us see now the application of reverse osmosis in purification of seawater. So after increasing the osmotic pressure, do you see now the water molecules now are moving away into the pure water molecules. So this is the pure water. Now the seawater remain there in that side, and here you'll now be having the pure water. So that is our application in relative molecular mass, specifically talking about the osmotic pressure. Now this is the end of our lecture today. So I welcome you. I'm sure that you have enjoyed Mati. Then I welcome you for the other day that we proceed with another topic. And the next time that will be now in organic chemistry and in a part of which is called the selected compounds of metal. And that part is also somehow making too difficult to some students. Some students are failing how to tackle those questions that are concerned with the selected compounds of metal. And basically, we will concentrate on the subtopic of carbonates of metal. So thank you for listening. You are warmly welcome. See you next time. Thank you.